So computational imaging is this idea that you should design your imaging systems in terms of both the hardware and the software together. So what's best done by optics should be done by optics. What's best done in digital processing should be done there. And often you do things like trade off having a very simple and cheap hardware and then use compute to do some of the work because it's very replicable and cheap. Or you might prefer to do it by optics because everything's analog there and you can get better performance. One of the most recent trends in computational imaging that I'll get into is this idea of data-driven design, where you not only use optimization and machine learning to process your images after you've captured them, but you try to optimize the imaging system hardware, so where to place the lenses, etc. This is typically the work of an optical design engineer who spends like a decade learning the black magic and is relying on heuristics. And now we can start to use these kinds of machine learning tools that are able to solve these gigantic problems to get at our imaging system designs. So let me give you an example. I'll talk about this project quite a bit. So this is a canonical example of lensless imaging. You have an imaging system camera, and you just take the lens off and you point the sensor at the world and take a picture. So your picture looks like garbage, but the light that hit the sensor is the same light that would have hit the sensor if your lens was there. The lens's only job is to bend the light rays in a particular way. And so the question is, if this is the same light that would form the image, can I form the image in the computer afterwards from this information? The answer is practically no. But I'm going to talk about this diffuser cam project where we put something in front of the sensor. It's a diffuser or a scattering element. It's like a bumpy piece of glass. Sometimes we literally use the stickers that you put on your windows so your neighbors can't see in. And you put this privacy glass sticker scattering thing on top of the cover glass of the sensor, and you take a picture. And it still looks like garbage, but now it's structured garbage. And from this image, we can reconstruct our scene computationally. And that's because that diffuser messes with the light. It bends the light, but in a random and unknown way. And so that's the whole goal, is to try to figure out how to calibrate that and then reconstruct the image. So this is one project amongst many in my lab. I'm going to get into it a little deeper because I think it's a fun topic for people to introduce to the subject of computational imaging. So let's think about a regular camera. So regular camera, you have some lenses, and then your point source in the world maps to a point on the sensor. So you're trying to design a camera to exactly map your world onto your sensor. And so we would say that the point spread function, or the impulse function, the system response function, is as close as possible to a point as you can get. That's like the goal of the imaging system. When we're talking about this diffuser cam, we have this diffuser or scattering element here, and so a point in the scene maps to some weird scattered pattern, almost like a speckle pattern. It looks like caustics, like the bottom of your swimming pool on a hot day, exactly the same effect, like random focusing of light. And it doesn't matter that this is not a point. It means that our image is not going to look like what you're trying to your scene, but you now have a mapping of how the scene maps into your sensor. So you can build this with like Raspberry Pi sensors and Scotch tape, and I have two awesome undergrads who wrote a tutorial on this and put it on our open source website, and we've had lots of people go and try this on the weekend. If you're inclined to do so, we love to see your resulting images. They're usually terrible because this is a terrible sensor, but it's fun. And you can do this with your kids. We've had a few people turn this into class projects at various universities. Okay, so we map a point to this weird caustic pattern. If I shift that point, what happens? That caustic pattern just shifts. That means the system is shift invariant. The system response shifts with the position in the scene. That's good. It's a really nice mapping. So I don't need to calibrate the whole system for every point in the scene. I know what's going to happen when I look at different points from a single calibration with a single point source. If I turn on 2 points in the scene, I get the linear sum of their intensities. This system is linear in intensity. It won't be linear in a complex field. So I can write this as a linear system. So y equals ax, y is the measurement I take, x is the scene out there, and a is this forward model or system matrix that describes how I map my world onto my sensor. So a typical camera, you're going after identity matrix for this A. You want to map your scene directly to your sensor. And this is what optical designers have spent centuries trying to do. When we're talking about computational cameras, who cares? This A matrix can be anything. As long as it's known and invertible, then it doesn't matter if it's an identity matrix. It doesn't matter what this measurement looks like. And so for this diffuser cam idea, you can trust me that it's going to be invertible, but it also needs to be known. So I don't want you to have to go and take an AFM measurement of your privacy glass sticker and make this super cheap, simple camera turn into something that you need a fancy lab for. I don't want to go and measure it. So I could go take my point source in the scene and measure it at every point. I don't want to do that. As I told you before, since it simply shifts, then we have this shift invariant effect where if I have one calibration measurement, then I don't need to measure all of them. Otherwise, I would have to measure like 5 million different points in the scene. I'd need a precise motion stage to go and sample through all of them. Or I could machine learn it, and I'll talk a little bit about that. We're going to do some mix of all three of these, actually. So when I move my point source laterally, then the system response shifts laterally. System is shift invariant. It means that this A matrix is actually a convolution, which means that every column of the A matrix is actually the same as the one beside it, but it's shifted a little bit. And so I don't need to measure them all. I just measure one with I put my iPhone flashlight in the far field and take a picture, and then I know the response. So it's actually clipping off the edge of the sensor here when you move to the side. We do account for that. I'm just going to ignore it here, but it's just an annoyance in our algorithm. But otherwise, this system is convolution, and we can do a deconvolution to reconstruct our scene. So we take the raw data and recover our scene. Here's a much prettier image. And then I'll talk a little bit about our algorithm. It's a big optimization. So we have this measurement y, and we try to minimize the difference between the measurement and the expected measurement after we put our current estimate through our forward model, subject to some constraints. So this is a non-negativity constraint, means I can't have negative light. That's obvious. That's just physics. And then this one on the end we can use to our liking to enforce priors or sparsity or whatever we want to enforce as constraints to help find the solution. Okay, so I'm going to call this like the physics-based way of solving the inverse problem. You put your measurement in, you solve this optimization problem, and you put your final result out. Usually the optimization procedure is some iterative optimization like ADMM or Vista. These are just like fancy names for ways of solving the optimization. The other way you could do this is like the new cool way to do this is to throw it all into a neural network, give it a whole bunch of input-output pairs, and let it learn how to solve for the reconstructed image. And it will do that. You can train a neural network to do this. So there's a lot of trade-offs here. And within computational imaging, this is a big trend, trying to replace physical models with machine learning, and I don't like it. Because you're taking all this physics that we know. I have a degree in electrical engineering. I spent a lot of time learning physics and optics. Why should I just throw that out the window because I have a neural network that can maybe do what I want it to do and probably gets things wrong a lot in very, very strange ways. But I can't negate the fact that deep learning is very powerful. And these machine learning techniques can sometimes do much better than physical models. And so what we want to do is find the best of both worlds. We're looking for a way to use both. So use the physics we know, learn the stuff we don't know. And essentially what we've come out to is this hybrid approach where the architecture of the neural network is a function of the physics. So the physics sets the architecture of the neural network such that it's an extremely efficient neural network, and it can learn to reconstruct the image with very little training data, several orders of magnitude less than doing like a pure deep learning approach. And so you're using the physics you know in order to constrain the network, and then you're learning the stuff you don't know, and you're learning these weird artifacts away. So here's an example result. So here's our ground truth. The physics-based way of solving this gets a bad image slowly. The deep learning way of solving this gets a different bad image quickly. And our hybrid approach is fast enough to be real time, to like sort of do this on the fly for a camera. And it has the least artifacts in the result. So this is a nice example of where physics and machine learning can and should work together. Okay, so I'm going to go back to just showing you a video from this camera. And I like to show this video because it's full of artifacts. This is not a high-quality camera image. So why would I ever want this kind of camera? It's a fun toy to have in the lab. It's a really cool concept. And you can make a camera that's very, very compact and very cheap. So you just have this diffuser in front of the sensor, means you don't need any space. So lenses need space, and the bigger the aperture of the lens, the more space they need, the further away they need to be from the sensor, the bulkier they are, and usually the more expensive they are. So this is cheap and small. That's a big advantage. But my iPhone has a cheap and small camera sensor on it that gives me much higher quality images. And so I actually believe that these artifacts are purely from like model mismatch. You know, the tape melted a little bit after you turned on the sensor and the calibration became a little bit off. And so I believe we could fix a lot of this, but that's not the direction we want to go in. We don't want to compete on quality with very high quality cameras that have been manufactured by high-resourced companies with a lot of people working on their camera teams and centuries of research behind them. What we want to do is look at things that this camera can do that other cameras simply cannot do. And 3D is my first example. This is the idea that if you have a regular camera and you focus on something, then that stuff is in focus and everything behind it is out of focus. It's just blurred. And the blurred stuff is lost information. You can't recover spatial frequencies that are gone. You can try, you can guess, but the information is fundamentally gone. If you think about these lensless cameras, there is no focus plane. So they give you this weird speckly pattern, but if you go to a different depth, they'll give you a different weird speckly pattern. And so the idea is that they just have a different response at different depths, and we can use that to capture 3D. And this is what happens actually when you move that point source. So this is actually just moving an iPhone flashlight in front of the diffuser cam. And what you see is that caustic pattern changes its scale. So now the scale tells you what depth something is at. And so you can go pattern matching. You go like looking for things that are a particular depth, will have a particular scale of this caustic pattern, and how shifted they are tells you their lateral position. And so we only need one calibration measurement still, and we can calibrate this whole 3D thing. Okay, so then we can write this as a big linear matrix. So I have this measurement that I'm taking on my camera. I have a forward model. Forward model is basically blocked up into convolutions for each depth. Each depth has a convolution with a slightly scaled version of the previous one. And we're now trying to solve for this X, which is like the scene in 3D. So it's like your two-dimensional image at every depth. Say there's 100 depths, you're going to have 100 times more data to solve for from the same measurement. So I told you we have this nice shift invariance model and the scaling with depth. So that solves our calibration and computation problem. But it's still severely underdetermined, right? Say this is 100 depths. We're underdetermined by a factor of 100. How are we going to solve this? And compression is how we're going to go. So everybody knows image compression. You take an image and you try to represent it with less data without losing sort of the information that's in the image. And this is almost always done in post-processing. But we're trying to ask how to compress that image in capture, at the capture stage. So why do we collect a 10 megapixel image if we're going to compress it to 1 megapixel JPEG? That means you collected 10 times more data than you needed to. But you didn't know what would be compressible or how it would be compressible. If you can have some idea of how to compress this data, you can do that in the capture stage. And this is called compressed sensing. It's been around for quite a while now. It's a really neat trick of math and science. It's not magic, it's science. But it's all about solving these underdetermined problems by using sparsity priors. So it's not magic in the sense that you are inserting information, that there's some structure in your image. So this is not going to work if you're taking pictures of garbage, just speckle noise. But it will work for natural scenes. It'll work for a lot of things in the real world. And let me just show you that our system is very amenable to this compressed sensing. So I take my raw image here, and I'm going to delete 80% of the pixels. So randomly choose 80% of the pixels and just throw them away. And from the data that's left, I can still get a pretty decent reconstruction. I can delete 90%. I can even delete 98% of the data. This screen's not showing well, but there's still a few non-black pixels there, and I can still get a sense of like what this image is. This is not normal for a regular camera, right? When you delete pixels, the information's gone. But this camera is highly multiplexed, meaning that a point in the scene maps to a lot of pixels on the sensor. So when I delete some of the pixels on the sensor, there's still information about that point in the other pixels. And so I still have a chance to solve this. So I'm still measuring less information than I'm trying to reconstruct, And the reason I can do that is because I have these priors about how sparse things are in a particular basis set. So this is total variation basis set. It means that the gradient of the image is assumed to be sparse. Okay, so that means we can not just throw away pixels on a 2D image, but use a 2D measured image, this gray thing, and reconstruct three-dimensional scenes. This is the reconstruction of a little leaf, and I'm just spinning the reconstruction to show you that we have pretty good depth information despite this being taken from a single camera. Okay, and we're getting about 128 depth planes at the full lateral resolution that we started with in the sensor. Okay, so this is really exciting for microscopy in particular, because microscopy, a lot of people are trying to image really big volume things with high resolution. And normally to do so, you use a scanning method. So you do point scan and you scan it across 3 dimensions. And so if you want to scan more voxels, meaning you want a bigger volumetric field of view or you want higher resolution, then you need to take more time. But now we can talk about our speed not scaling with the number of voxels you want to reconstruct, but the number of important things. So maybe if your sample is mostly zeros, then it's the number of voxels that are non-zero. Maybe it's the number of features in something. So this gets really exciting for thinking about particularly like fluorescence microscopy, where you're tagging things. So they have these fluorescent molecular tags, and each fluorescent particle is like one non-sparse thing. So if you have a big 3D volume, it's very unlikely that the whole thing is full of fluorophores. And so you can start to look at getting very large space bandwidth product images. A space bandwidth product is basically just the number of voxels that you want to have in your reconstruction. So it's the resolution and the field of view together. And so if you wanted to go fast and past, then you can, there was single shot methods with light field microscopy, single shot 3D, but it drastically sacrificed your lateral resolution. And what's the point of a microscope if not to get better resolution? So now we're talking about keeping the resolution and getting single shot 3D if your sample is sparse. And how sparse your sample is tells you how far along this like curve you can go. Okay, so one of the key applications we've been pushing this towards is in neuroscience. We work really closely with Hillel Adesnik's lab in neuroscience at Berkeley. And we want to take like these big microscopes and instead replace them with this simple lensless microscope because it's lightweight and cheap. We can make a whole bunch of them and tile them sideways and look at a mouse's brain while it's behaving. So when the neurons fire, they light up. And so each neuron is like a little point source in 3D. And if I can do 3D mapping, then I can tell you which neurons lit up at which time. And I need to do this at the time scales of the brain, which is milliseconds, which is no problem if you're doing single shot 3D. So here's an example of a slightly different optical setup. But this microscope is looking at the neural activity in a zebrafish brain. You can see the 2 side lobes of the brain here. And each of these dots represents the 3D position of one neuron. And the colors over time are telling you which ones are activated when, or when they're firing. So this zebrafish isn't doing anything special. Hillel is the neuroscience expert who is using this to try to decipher how the brain works. He has other tools for forcing one particular neuron to fire, and now we can watch which ones it causes to subsequently fire and see how they're connected. We did this all in a sort of the lensless package where you just have this sensor that you can put right up against the animal. This is a zebrafish again, and you're seeing the neural activity where each neuron, as each neuron fires, we can locate it because we have better than single neuron resolution, which is a couple microns. And then one more example, the raw video, and then some reconstructions of these little water bears. So this is a collaboration with UCSF. Saul Cato's lab is trying to look at the locomotion of these little fluorescent water bears. And they need high resolution, but they need to get it across a big volume because they want to watch this thing swimming freely in a little tank. But it's going to be extremely sparse because there's just this little guy in a big tank. Okay, so I'm getting towards the end of this topic. And I want to get to this end-to-end idea, or the data-driven design ideas. And previously, people had done a lot of work around optimizing the image reconstruction algorithms. as I showed, we can use hybrid machine learning with physics to optimize the reconstruction algorithm, but now we want to optimize the actual hardware. And for this diffuser cam, that amounts to optimizing the diffuser. So instead of taking some opportunistic off-the-shelf diffuser, we are going to instead take an approach where we just allow it to design the diffuser. So find the best diffuser. What's the best surface shape for a piece of plastic that's going to go over the sensor in order to reconstruct some 3D point sources here. So this is our 3D volume, has a bunch of point sources. We're going to optimize it for some sparse set of point sources because we want to use this for the neural activity tracking across a particular volume. And this is like the iterations of the optimization of the design. And you see the design actually comes out with about 8 of these little micro lens arrays. And we can talk, I'm happy to answer questions about why it comes out with this. We've talked a lot about that. It's really interesting. But it's not really a diffuser anymore. It's more like a random micro lens array. And each of these have different focal lengths to help you with the 3D. Okay, so that's like this diffuser cam project. That's like one project within my lab. I want to talk about another one that's a little older but gives you a nice flavor of where the world of computational imaging is going. And you're going to see a lot of the same themes across this one. So this one is a real microscope now. It's not a lensless microscope. This is like the oldest infinity corrected microscope you could buy when I started my lab, and I was being really cheap. But it's just a basic bright field microscope, and we've made one hardware change. We took out the illumination unit, and we replaced it with this Adafruit array. So it's a 32 by 32 array of LEDs, RGB LEDs. It's literally a kid's toy. Adafruit's a kid's toy company, controlled by microcontrollers. We get high school students who know how to program these all the time. And the idea is that I'm going to place this above the sample. It's big. It's like 5 inches by 5 inches. And I place it a few centimeters above the sample. And then I'm turning on different LEDs. And as I turn on each LED illuminates the sample from a different direction. So at the sample, you always see this flat, homogeneous light, but it's coming from different angles depending on which LED I turn on. So this is patterning illumination angles of the microscope, or you can think about it as source patterning. Later we'll get into that we make much fancier big domes of LEDs, but the idea is that by patterning the illumination angles, I can make this really neat computational imaging platform where I can do all kinds of different imaging modalities simply by choosing which LEDs to turn on, capturing some pictures, and then doing different post-processing on those images. So I'm not going to get too much into this multi-contrast, and this stuff some of this was originally introduced by a group at Caltech, and we've taken it a lot further. But the idea is that if you turn on most of the LEDs, or just a bunch of LEDs, you get a bright field image, so it's just like a regular microscope. If you turn on the LEDs outside the circle of angles that pass through the microscope, that's set by the numerical aperture, or NA, of the microscope, then you get a dark field image. And if you turn on half of the bright field circle LEDs, you get a phase contrast image. So typically, these are the 3 most popular non-fluorescent contrast modes for a microscope. And normally, to get dark field or phase contrast, you'd have to put in a specialized objective lens and possibly something in the condenser plane as well, which is expensive. It takes a long time to swap them out. Now we just switch which LED we have on. And then you can swap between them really quickly and take videos that basically capture all 3 at once, which is something you couldn't do when you had to physically change the hardware to swap the different contrast methods. So here's an example of our quantitative phase reconstructions, where we're going to take a couple of images from different illuminations and then reconstruct quantitative phase. Quantitative phase is a measure of the optical density, which is basically like the physical density. And this gets at what I think is probably the coolest thing that this LED array microscope can do. I'm calling it gigapixel imaging. If you want to be fancy, it's called Fourier tychography. But basically, it's going after the problem of really big field of view with high resolution. So microscopes, just like cameras, have to either zoom in to get high resolution across a small area, or zoom out and get poor resolution across a big area. And the reason we can't have both is money. You can pay a lot of money to correct a lot of aberrations. So aberrations are the limiting factor in microscopes. You can pay money to correct those aberrations. At some point, there's diminished returns. So lithography lenses pay a lot of money to get rid of a lot of aberrations. They can do this, but a regular microscope can't sort of scale that like that. And we're not going to actually break this we're not really breaking the diffraction limit to get this higher resolution. We're circumventing it. We're going to take a bunch of images. So we take this like low resolution microscope. We take the lowest NA objective we have, which means it has a big field of view. And so we're getting a big area. But if I zoom in, I just am not resolving the smallest features because the resolution limit will be worse for this microscope because it has the big field of view. So then I turn on my disco pattern of LEDs, and I take a bunch of low resolution images, and from this low resolution video, I can reconstruct higher resolution. There's about 7 times higher resolution in each dimension, I think. And how do we do it? This is why I asked about Fourier transforms. So most people said they know what Fourier transforms are, so this is going to blow your mind if you don't know it already. But if you put a sample in your microscope image plane, and you look in the pupil plane, which is also called the Fourier plane, you will see the Fourier transform of your original distribution. So then when you go to the, oh yeah, that should blow your mind. And then you go to the output port of the microscope where you put your sensor. This is like the objective, and this is the tube lens. And you do another Fourier transform. So if these lenses are placed correctly, then this will be a Fourier plane. And then you do a second Fourier transform. 2 Fourier transforms does what? Nothing. The inverse Fourier transform is just Fourier transform flipped. So your image will be upside down here. That's why images are upside down. Flip your sensor around and you won't even notice it. And then you got back to your image plane. But now you have access to the Fourier plane. So now I can talk about the sample's Fourier plane. And if I look at this like big field of view microscope, it always has a low numerical aperture. That means it has a small bandwidth. It's collecting very small range of spatial frequencies. So the bigger this green circle is, the better resolution I will get in my image. So big circle means high resolution. This is the spatial frequency spectrum of this sample. So green is saying how much spatial frequencies I'm collecting in each image. When I light up a different LED, the cool thing is it's illuminating by a tilted plane wave. In Fourier space, that's a shift. So you shift which part of the spectrum that you collect at the camera, which means you collect information from sort of sub-resolution features. So like all these lines here are from features that are below the diffraction limit, but it's still a low resolution image because I'm still capturing only within that circle. So basically I'm going to go light up every LED. Each LED captures a different portion of the spectrum, and then I can build up this much larger bandwidth representation of the image, which has higher resolution. So this is called synthetic aperture. The hard part is that what I'm measuring is intensity, but if I want to do a Fourier transform to get the high resolution image from Fourier space stitching, then I need to also have the phase. So we need to also do a phase retrieval. That's why these circles are all overlapping. That allows us to do a phase retrieval and write the whole thing as a big giant optimization, much like the diffuser cam idea, except now we're optimizing to solve for the complex field of this big stitched Fourier space to have phase and amplitude. And once I have that, I just do its inverse Fourier transform, and I can get the reconstructed scene, and I get its amplitude and its phase, which is really important for cells because typically cells don't absorb much light, so their amplitude distributions just look like nothing. Cells are invisible. This is why we stain and tag cells. If you do like a cancer biopsy, they'll stain it. It's like really old school. They could just do quantitative phase imaging and be able to see them. But some of this medicine is still working on very old principles because it works for them. So this quantitative phase is just sort of like a freebie. How you solve this inverse problem is really important. So first order optimization or gradient descent is sort of go along this path of steepest descent and look for the minimum. These problems are not actually convex, but it works okay. If you use second order optimization, meaning you take the first derivative and the second derivative of the cost function, you can get a much better result, but it's super slow. So 100 seconds, and this is only a tiny patch of that big, gigantic gigapixel-sized image. So here's some commentary on speed versus accuracy. So what we actually want is the dog that goes as fast as possible but still makes it in the door. And that's this quasi-second order method. This is a Gauss-Newton approach. It's actually really cool. It's basically, instead of taking the second derivative, which is a humongous matrix, is a Hessian, we're just going to look at the diagonal of the Hessian matrix, and that's enough to help us do the update. Okay, so now we started to think about like what things can we look at? And everyone in biology wants to do live cell biology. So we're limited in time, right? Because we want to look at these live samples, and being label-free so we don't have to tag or stain them means we can look at live samples, but we're going to run out of time. Like if we need to capture 200 measurements, then we really can't look at stuff that's happening really fast. So we kind of have to think about which samples we're going to look at, and the number of measurements you can take before the sample has moved appreciably needs to be taken into consideration when you decide how much super resolution do you want versus how fast you want to capture those images. We call this space bandwidth time function. So this is like sort of like a careful trade-offs as you do each experiment. But we can win this game too. As I said, these circles in the Fourier space, they have to be overlapping. Otherwise, we can't do the phase retrieval. We can't solve the inverse problem. It just won't work. So we can't reduce the number of data we take by just taking less images. And so with this overlap, we basically are capturing 10 times more data than we're reconstructing. This is exactly the opposite of the compressed sensing I talked about before, where we're reconstructing 10 times more data or 100 times more data than we're capturing. So this is not a good situation to be in, but it's not obvious how to reduce the number of images we capture. And so I'm not going to get into the details, but basically you can turn on those half circle LEDs and capture like twice the resolution. And then beyond that, we turn on 8 LEDs at a time, and then we can take 8 times less images to fill in the whole Fourier space, and that's what that disco pattern you saw before was. So this is our heuristic design. So half circles in the middle area, and then randomly chosen 8 LEDs outside. But actually, we can do this end-to-end machine learning design to try to learn what are the best LEDs to turn on, and this is what it comes out with. Kind of cool. It's a little bit similar, a little bit totally different than what we had heuristically designed with our decades of optics knowledge, but it works way better. So if I take normally I would take 89 measurements, different images as I turn on 1 LED at a time, but if I shut it down to 10, then our heuristic design performs poorly, but this data-driven design actually does pretty well. This is another speed up of factor of 10. Plus, we're turning on 8 LEDs at once, means 8 times brighter, so we take 8 times shorter exposure. So we're getting massive speed ups here, several orders of magnitude, which allows us to finally look at live cell samples and still get this very large area, but high resolution. So this field of view here is the field of view that you would have had with an 80x microscope objective. We're getting it with a 10x objective, the resolution we get is equivalent to that from an 80x microscope objective. So you get all this extra area for free, or you get all this extra resolution for free, however you want to think about it. And this is all quantitative phase results, and these density maps essentially let us do really easy segmentation on these images. All right, so I still have 10 minutes, and now I can get into my favorite part, which is talking about all of the problems. And I could just end the talk there, leave you thinking that this all just works, but it does not. And let's think about, particularly, this is a nice quote with respect to compressed sensing, that when you try to do things like compressed sensing, like taking less data, you get faster capture. You get more efficient imaging systems, but that efficiency comes at the cost of fragility often, where you're capturing less data, then each data matters more, every error hurts you more. And so we need to think more about robustness. So our computational imaging, we often model as this y equals ax, like a linear system. And this A is like the heart of everything. We're designing the optical system. We know the optical physics. We know how this system should perform. And so we can know this A matrix. But in reality, you have some misalignments, etc. The A matrix is not quite what you thought it was because you made an approximation or you misaligned something, etc. So what we spend a lot of our time doing is calibration. And there's a lot of discussion in computational imaging in the last years about how is our stuff useful if there's only like one postdoc in the world who can perfectly align the system and nobody can build this at home and use it. And so I got into thinking about this because we work really hard to make sure our systems are accessible, that you can build them at home or in your lab, et cetera. And we got into this talking about like reproducibility, that not only do you have to make the hardware cheap and the software open source, you also have to really think about like how robust is your system. And I think that this is a really important topic that we don't talk about enough because it doesn't come into, there's no theory for this. So we started thinking about, for this LED array system, we know what the problems with our A-matrix modeling are. Our aberrations in the microscope and the LED position. So when I think my LED is coming in at a 45-degree angle, actually the sample's floating in water and there's some refraction at the surface, so it's actually 46 degrees. And that can be enough to throw off your whole reconstruction. So we calibrate all of these LED positions and the aberrations, and if we don't calibrate them, we don't get back this super resolution that we've been after. So it's extremely important. So we can sort of like write our A matrix as a function of all these calibration parameters that we need to measure. And these are the important ones for this system. But Regina is like my toddler saying, I don't want to calibrate anymore. It's so annoying. It takes forever. It makes the system not usable. And so what we want to do is algorithmic self-calibration, where we not only solve the problem for X, which is our measurement, our scene that we're trying to reconstruct, but also let's solve for these parameters of the forward model. Let's just take some extra data and solve for both at once. And this is joint optimization, is very well known. And this works great. So you can see here, this is our recovered phase with the higher resolution, and we've also recovered the aberrations. So we just solve for the pupil aberrations. This is like the wavefront aberrations of the microscope. Those wavefront aberrations actually change depending on which part of the field of view you're in. So you can solve on a patch-by-patch basis, which is really important for these gigantic, cheap lenses because they do poorly at the edges of the field of view. Okay, so my last thing that I will get into is how we can do all of this in 3D. So everything I've been talking about is really assuming that your sample is some cells on a plate or a petri dish. That's pretty much a monolayer of thin cells. So when we come in at different angles, I said it shifts in Fourier space. That's not true when you have a thick 3D sample. When you come in from different angles, you actually project through the sample in different ways, much like tomography. So we can take all the lessons of tomography and sort of add them on top of everything I've been talking about. Here's an example of a 3D reconstruction for some mouse embryos. You're just seeing different depths as I go through this video. And this is the refractive index, so the density. In particular for embryos, you want to grow them further, and so you can't stain or dye them. So these kind of quantitative phase measurements are really useful because they can't use other labels. Okay, so the 3D problem actually is really cool. It amounts to a gigantic neural network. And some people have pointed this out for a long time, that these kinds of models are very neural network-like because you're trying to solve for the absorption and the phase or refractive index at every 3D position within the volume. So you're training this big neural network, and then once you find the weights of the network, that is your answer. That's your reconstructed image. So just like all of the neural network problems, it's highly nonlinear, very non-convex. We have no idea whether it's going to converge, but heuristically we know that it does when you have that Fourier overlap sufficiently. So when you take enough illumination angles and you have a sufficiently good model for how light propagates through the sample, which we work on a lot. But the cool thing is we can actually model how light is bouncing around inside the sample. It can bounce around many times. So multiple scattering in optics is roughly considered intractable because you can't mathematically or analytically solve for multiple scattering. It's a highly nonlinear process, even in terms of the complex field. But we can now model it in our forward model, which means we have a chance to solve for it in the inverse problem. And I won't get into how we do it. It's not much different than the 2D case. But here is a gigantic 15 gigavoxel reconstruction of a C. elegans worm. And I'm just showing you the refractive index map of the central slice of this 3D reconstruction. And I'm showing this because it has a lot of contrast here. So there's a lot of refractive index changes in this, throughout this sample, and they introduce sample-induced scattering. So this is the end of the worm, and you're going to see it come to different depths to show you that it's 3D information. And all this scattering caused by this refractive index changes would otherwise make all of our images focused into the center of this worm be sort of like completely unintelligible. But now we have these models for multiple scattering. We can actually reconstruct things through highly scattering samples like this. Okay, so this is the end of my talk. I'm actually early, and I think you probably get a thread from this that my lab is really obsessed with making sure that our imaging systems and our techniques are very usable. So somebody in a biology lab could build this and use this. The LED arrays that I talked about, the toy ones from Adafruit, are really not practical. You can only have one LED at a time. You have to use duty cycles. It's really annoying. So we started building our own and outsourcing their production. So we just mass produce them. We outsource the production, mass produce them, and then sell them through this small startup company. So you can really easily get one and click it into your microscope condenser lens sort of on the fly and try these methods out. But also like this diffuser cam idea, we've had a lot of people take this on for fun projects. And we're sort of always looking for new ways to make our work more accessible and easier to use in the real world. And we've been really excited about people who've taken this on for various things. And I'd be happy to talk to anyone who has ideas for things they might use these microscopes for. So thank you very much to my group members, all my students that did the work, my collaborators, and my newest anti-collaborator, who I really enjoyed being away from last night.